We'll get started. Thanks, everyone. It's a pleasure to have Andrew Wang joining us from the University of Edinburgh. Andrew's a PhD student working with Professor Mike Davies on imaging inverse problems, self-supervised learning. One thing in particular is that they developed an open source library called DeepInverse, which facilitates doing deep inverse problem type research in PyTorch, so it kind of combines the world of reconstruction and machine learning. And I believe all of the things you're showing is implemented there. But today you'll talk to us about solving imaging inverse problems without ground truth. All right, thanks so much.
Cool. Thanks everyone for joining. So I am Andrew. I'm from the School of Engineering in Edinburgh. But the next slide is a bit about Edinburgh, but firstly a bit about the talk. So I'm going to talk about a set of problems called imaging inverse problems, which might be familiar or might not be familiar to you. So by the end of the talk, you should be familiar with inverse problems. We should be all on the same page. And we're researching how to solve these with deep learning, which has been very popular, and there's a lot of stuff in UT Austin as well. For example, in John's group, solving these kind of problems. And specifically, I'll talk about why we want to do this without ground truth. And because I'm an engineer, I motivate this by real-world problems. So there are real-world problems where we want to do this without ground truth in, for example, medical imaging and scientific imaging. So hopefully you go away with a sense that this is also an important set of problems to work on. So I'm based in Edinburgh. So Edinburgh is a very beautiful city. If you've not visited before, it's a very nice place. So Edinburgh is like in Scotland, which is in the UK, so just north of the border with England. So I'm from England originally. So this is a massive kind of crag in the middle of the city, which you can walk up, and then you have a nice view all over the old town. It's like a complete contrast with Texas, which is kind of a bit of a culture shock for me coming here. So you can you stand here, which is like half-hour walk up from lecture halls, and you can see the Edinburgh Castle. You turn around, you see the North Sea. It's just a stunning place. Although that doesn't translate into office spaces, and my office is quite ugly compared to here. It's just so beautiful here. So. Okay, so I'll talk about what is an imaging inverse problem, so we're all on the same page. So I've just been, for example, this week in ISPE in Houston, and it seems to be a bit of a confusion about what are the kind of exact problems that we're talking about in image reconstruction. And why do we want to do this without ground truth, and how we do this in our research, and in some case studies for some real examples, so across environmental and medical imaging. And I'll talk about what we're doing in the open source software. So even if you're not working in this exact field, maybe there's some commonalities with your own software, which is something we're trying to push towards. And then finally, some directions, which is linking to some of the stuff that's active research that's happening in our lab, but also around the world, for example, in UT Austin as well. So an imaging inverse problem is, the goal is to reconstruct, to get high quality images or signals, for example here videos, and then in the context of medical imaging, for example, scientific imaging, this is the first step before downstream tasks. So your medical image analysis, for example, is where they take this and then they segment the tumors or segment the cells, or in microscopes or in satellite imaging, you have to get high quality images first before you do any classification or segmentation, or now you're doing VLMs or whatever fancy stuff you're doing now. But this is kind of the first task that happens. So why do we need to do this? Because the machine itself, the imaging device, only captures what's on the left, that's the measurements. And these tend to be noisy or have artifacts or low resolution. And this is due to the physics of the imaging scenario. So in an MRI machine, you lie in the MRI machine and then it scans you. And you either need to wait a long time for it to fully scan you to get high resolution, or now we're talking about accelerated MRI, so it can do faster MRI scans and then capture less information, so leading to a lower resolution, noisier image. And then the goal is for us as researchers to reconstruct a high quality image from these low quality samples. So in this particular case, on the left is a 8 times accelerated MRI scan, so we are losing 7/8 of the data, and we're only keeping 1/8 of the data, and from that we need to reconstruct the full quality image. So mathematically, going from right to left is described as a forward problem, where you pass it through a map. So in the MRI case, A is a linear operator, which models the MRI machine. So it takes the frequency samples as a Fourier transform, followed by a subsampling mask. And so this typically has a non-trivial null space, or is ill-conditioned. So we have an ill-posed problem going forward. This is why it's not trivial to just take the inverse of the matrix A in a linear case. And then furthermore, the forward problem is also contaminated by noise. So eta here is a noise case. In an MRI, we typically model this with, for example, Gaussian noise. And we can't then just trivially do the inverse of the matrix. So then the goal here is to construct a solver F that takes us from this Y to X, to reconstruct the images. So just as some examples, dynamic MRI is quite a nice example. It's very, very hard. The heart is beating at a rate that is much faster than the MRI acquisition to fully sample the space. This is a very tricky problem, and it's got applications not just in cardiac MRI, but kind of free motion that's not periodic. So this is like of the liver, of the lungs, and of speech. In another setting for MRI, we're looking to make smaller and smaller machines so that you can bring it to the point of care, to the patient side, rather than taking the patient to the hospital. And with smaller and smaller machines, then the images get noisier and noisier. So your eta term, which is a Gaussian noise, or Gaussian sigma, is getting bigger and bigger. So we need to reconstruct in these very tricky scenarios. Another inverse problem, which is very challenging and very real, is in satellite imaging. So again, it's the exact same framework. So these are what we want to reconstruct. So this is what you see when you go on Google Satellite View, and this is a multi-channel, so for example, 3 or 4 or 8 or 16 channel image at high resolution. But the satellite in the sky is only capturing either one of these or both of these two. So this is a grayscale, so single channel high quality image, and a very noisy low quality multi-channel image. So you can see that by going the forward problem, by going from right to left, we are losing color in the high resolution and losing resolution in the full color. And so it's not trivial to reconstruct it. So these are both two important problems. And what's common across both of these problems is that in real life we never have ground truth of these things. So for example, taking this example, the satellite never sees these images on the right. So anytime we try to train a supervised learning model, we never have these X's as ground truth, because we never really have we never have this data in the first place. So typically supervised learning will have to train with these kind of images generated via some kind of pseudo gone.
So why do you have this image?
Yeah, so it's generated via some kind of classical method, which has to make lots of assumptions. So for example, in the MRI case, maybe it's clearer. This, you might think that this looks like a ground truth beating heart, but this is a strictly periodic beating heart. And this is created by, it's not a video of a heart anymore. You have to take multiple periods of the heart. So you have to wait, for example, 20 beats of the heart, and then fill in the blanks by enforcing that the heart is beating periodically. And this is kind of the classical way of doing cardiac imaging. But then you can imagine, so you have this kind of fake ground truth. Anytime you train with this kind of ground truth, the best that you can get is a regular beating heart, right? Then you can never image a periodicity of the heart. So maybe this is why I'm not talking about static MRI case. In like knee MRI, for example, you keep your knee there. If you wait long enough, you will be able to get ground truth because it can sample enough. Similarly, if you had a big enough satellite in the sky, then you will be able to get a high quality image. But in these cases, this is impossible. But yeah, thanks for the question. Very good question.
So if you have a normal image, can you augment it so you can get like an abnormal image?
What do you mean by
like data augmentation? Can you use that technique to get like image, rare image?
Yeah, you could, but that's kind of a philosophical thing in that if you don't ever have you will never be able to create reality in a way. Like you could like morph this to make it aperiodic, and that's kind of like synthetic data, right? But in imaging, we're not. Some people are talking about like how to make images look nice, and we use synthetic data. But in kind of scientific context, we really want to get something as true as possible to reality. So yeah, it's another example of kind of the newest generation of satellites, people building satellites smaller and smaller. We want to build these so they're cheaper, they're faster, they can move around the Earth faster. So as I said, with supervised learning, just to summarize, we are training with ground truth images, and the ground truth is either impossible in these two cases or expensive, impractical. So for example, with near MRI, I can lie there for long enough, but a child might move around, for example, so that's more impractical. Okay, so now we talk about self-supervised or unsupervised learning, which I'm going to use interchangeably. So the kind of most naive, the first kind of basic initial thought about how to do this is we reconstruct our images and we map it back through the forward operator to get our kind of remapped Y, and then compare these to the MFC instead of comparing X for the ground truth. And then we can think like, oh, can we train a network with this? The problem with this, you can probably quickly think about, is that because A has a non-trivial null space, any vector in the null space of A that you add on to X will be trivially mapped back to 0, so that you can get precise 0 loss with an infinite number of solutions. So this is not good. You can imagine like a very simple MRI in-painting case. So you have an image and you block out the face of the person, but if you just train with this loss, then you can only enforcing consistency outside of the mask bit. You can never learn what's inside that. You have to, we have to do that in another way. As a side note, what do we not mean by self-supervised learning, just in context or the wider machine learning context? So self-supervised, I guess, in most of the literature, the words self-supervised and unsupervised are used a lot in the image analysis and representation learning communities. So in this case, your ground truth is your labels of your dog or cat, for example. But in these kind of literatures, you're still assuming that you have your high-quality images. So we're saying we have no access to our high-quality images X. Perhaps more closely related to our field is in diffusion models. So kind of the diffusion model way of doing this kind of thing is you have a pre-trained diffusion model which you download from Hugging Face, which is very well trained, and then you use that and you sample from that diffusion model to solve your inverse problem. And then some people say that's self-supervised in the literature, but they are ignoring the fact that this diffusion model itself has been trained on lots and lots of ground truth images. Let's say tomorrow we want to start imaging a new galaxy or something that we've never seen before. That's going to be out of distribution for the diffusion model, right? So you're suddenly having to say, we never have these images ever, so we need to train
I guess
something
it
else.
depends. If you've trained on other type of stellar images, then it may not be out of distribution. And like from what I understand, like for MRI, John, correct me if I'm wrong, but like the diffusion model that you used was trained on like only 12,000 MRI images.
Yeah, but it's still, if you're using it, if you're
Is
training
the
a model
12,000
on
number,
brain,
is the 12,000 number right?
the number?
Like that's what Brett told me.
No, it's 10,000 samples, but it's like ordered 100K or something. It's 10,000 volumes, but each volume has,
He told me 10,000 scans.
but a scan is not an image.
Oh, okay, but I'm saying it's surprising that you only sort of need 10,000 scans.
Yeah.
It's a philosophical thing as well that, okay, maybe in most imaging things that we see in our day-to-day lives, yes, the diffusion model captures these features or the information in these images, but we're trying to push the boundaries of imaging here, right? So imaging smaller and smaller things, for example, cryo-electron microscopy, imaging going smaller and smaller. You could, I mean, it's a philosophical thing that you could say that a well-trained diffusion model or a well-trained foundation model can capture anything that we've never seen before, but you can always construct extreme cases. So, for example,
Sure, I'm just saying it's highly domain specific.
Yeah.
But even in your example, I still need the images to train, right?
Yeah, but I would have thought of, I mean, it would have been hundreds of thousands. I mean, there are millions. You're training them all with millions of parameters, right? And you only need like 10,000 scans. I mean, it's kind of surprising.
It's more than 10,000 images.
Okay. 10,000 scans.
Okay. Okay, so I'm going to now try and categorize all the different kind of frameworks of ways we're solving this problem in the literature right now. And maybe the citation is a bit of a spoiler. So the classical way of doing it, before deep learning came along, is you have an iterative optimization procedure where you constrain your measurement consistency or your data fidelity, y minus ax, and then you add a regularizer term onto it. And this regularizer term is enforcing some quality of the image. For example, your image is varying smoothly, for example, or is piecewise linear, for example. And this is okay, but then you have to really make this very specific to what you're imaging. And at some point, it's gonna break down because you can't learn. You always have to go from your belief rather than learning from data. But the good thing about these methods is that, it's a traditional solver method. You don't use ground truth because you're not doing any learning. It's kind of iterative machine learning models which have come out, which are trying to be inspired, so kind of physics-inspired machine learning, where you're kind of being inspired by the iterative optimization, but you replace some part of your optimization within your network, such that you can do like your traditional optimization, but you are also learning at some point. And I'm placing all of these listed here into this context. So in a diffusion sampling stage, you are sampling with an iterative procedure, but then one part of this iterative procedure is your diffusion prior. Similar with GANs, and a lot of these are kind of a lot of methods that have been proposed in the past few years. On the other side, there's feed-forward machine learning methods, which is kind of your standard machine learning when you first take a machine learning course. So you have the neural network, you pass in something as input, and then you have something as the output, and then you compare that with your ground truth. And then this is what I was showing earlier on the 2 slides ago. And then now there have been many loss functions as well proposed for this kind of training. And people like this training because it's I like this training because it's relatively simple. You can train a network very easily for many different contexts, and it's very quick for inference. Right? The benefit of feed-forward networks is you feed your input and you get your output. One step and you get your reconstruction. There's no optimization at inference time, and there have been some research towards this direction, and I'll be talking a bit more about this later. But there's a gap here, which is also I wanted to mention for this talk. Is iterative methods that you can not use. There's no ground truth for using these methods. And I think there are pros and cons comparing. And no one really has compared these two paradigms before in the ground truth-free context before. So you can now train diffusion models without access to high-quality ground truth images, as of a few months ago, I guess, out of UT Austin. And then you can also... For MRI, okay, for real imaging problems a few months ago. And they're also kind of related, so you might have heard of the deep image prior, which is still very popular, where you regularize your reconstruction within your networks. You believe that the weights of an untrained network has some regularizing properties. Okay, so a breather before talking about what we're doing. So just kind of my main research is focused on this line, so the final line here. So how can we train feed-forward networks without ground truth? Which seems like from the initial step impossible. From this step, it's like how can you learn something new if you don't know what your targets are? So what we are doing in equivariant imaging, which was proposed a few years ago now, is we impose a belief that the unknown set of all images that we're trying to image is invariant to some kind of transformation. So on the left, there's an image of a knee, for example, and then we believe that when we rotate the knee, that's also a knee, and that's kind of biologically plausible. But we never see these during training. So it's kind of very similar to data augmentation, but we don't see these during training. We can't enforce this directly at the input. But we have this belief so that for all x's in this unknown set of images that we don't have access to, we have this group invariance. So for example, here we've got a rotation group. this works kind of most intuitively level, and this works because let's say you have A and you can expand the identity. You are now imaging the image set, so the X prime here is combining T and X, but X prime is also in our set. And now you're imaging your set with not just your operator from before, but a whole now set of virtual operators, A prime, which is of the same order as the group. So you can imagine, like, now you say you have a null space where the black lines are, but now because we're transforming it, you can also image the null space stay the same, but the image operating is changing. So we can enforce that using our loss.
Sorry, I didn't get it. Like, for example, if I'm doing X-ray crystallography, it's certainly rotationally invariant, but like it's still noisy no matter how I rotate it. Like, why is that doing any sort of natural T-noising?
Okay, maybe if I explain this and then you ask, maybe this will elucidate it for you.
Okay.
Okay. Maybe you can convince yourself at least. So yeah, we have this. We have access to this set of operators, right? So ignoring this is what we had before. So this is measurement consistency. But now during training, we transform our reconstruction, and then we pass this back through the entire imaging system, so the composition of F.A, A.F, and then we are comparing these two with each other. So now we are saying that these two can be. Are you okay? Now we are enforcing that now that the transformed images are also produced by the same imaging system.
Was this supposed to convince me? I'm not
convinced.
convinced. You're giving the talk, because you're not going to convince me. So, you know, if I have an image and it's blurry and I rotate it, every rotated image is also going to be blurry. So why is there some denoising going on?
Okay, maybe a blur is harder to imagine, right? Let's think about the in-painting case, right? So let's say you have a you have a face of a celebrity and you're block masking out the face. Okay. Then if you rotate your operator and then you image the same ground truth, then the null space is going to be a different place, right?
Oh, so you're, yeah, but what all you're saying is, oh, well, there was something missing here, now I rotated it, I get the same operator, now it's not missing. So
yeah, exactly.
Yeah, but that doesn't happen in these data sets. Like, if I have one face that's blocked out, like, I don't get to see that same face with this unblocked out and rotated.
Yeah, I mean, we're talking about a set of images here. I'm not limited to the finite data setting so far, right? But then you think about if you have your data set of faces, survey data, for example, can you enforce invariance? Like, can you believe that a rotated face is a face that we believe that, yes, but in the context of the data set, no. But then you can think, okay, that's a very kind of pathological data set in which that's not a data set of faces anymore, that's a data set of centered looking forward faces, if that makes sense. But if you have a data set of hearts at arbitrary orientations, then you can impose this belief.
Okay, but what about blurring?
Okay. For blurring, it's more complicated because you don't necessarily have for the pure blurring case, you don't have a null space, but then you have this the ill conditioning. So it's a different but parallel argument. We can talk about it afterwards. So I don't want to get too much into the details right now. Otherwise, we can go forever. Happy for now?
I mean, this is more like, if you think about ambient diffusion with adding noise or like corrupting the operator a second time, it's kind of like that, right? Like there's a reconstruction X hat that only saw one operator. You don't get to change that.
Of course.
But then you take that reconstruction and you apply a new operator that rotates that image first.
Yeah, I mean, we could generalize this as well.
Sure, but ambient works because of Tweedy's formula, because I know that I can add more noise, and so I have a velocity field that points in the denoising direction. This is not adding more noise.
The noise part, I think, is separate. It's about how you're augmenting the A operator, right?
That's kind of the core.
Like this is also in a noiseless setting. It's just to say you can observe the same. You can have a loss on a reconstructed image twice by applying a different A operator. Right, like you still expect the same image out.
Sure.
But here the A operator is the same. All you're doing is rotating the image, if rotation is an invariant.
Yeah. you can generalize this as well, like if you have multiple A's in your operator, so you have multiple masks in your MRI data, for example, you don't even have to use transforms, you can just select another operator from a set of operators. So
okay, I guess my question, can you prove, for what class of operators can you prove that, like, you actually learn in the limit, like, the correct?
Yeah, I mean, we have conditions on the operators, so.
What is, like, roughly what are the conditions?
So one interesting condition, which also this helped me originally convince myself, is that the operator A cannot commute with this itself. Because if they commute, then you gain no more information. Because then you rotate and then you masking out the same as masking out and rotating.
Okay.
So in an MRI case, you can't apply shift, for example, because the Fourier transform is a shift invariant operator. Okay, go on.
So is the idea that, so it turns out theoretically that the optimal loss bound is invariant under G, and averaging over the Lie group gives you an estimate on the minimizer, which is G invariant, and that is a good candidate for the minimum loss. Because the minimum loss cannot depend on the coordinate system in which you define the data.
Yes. I've not thought about it from that perspective. But yeah, I mean, the original reason why this should work is, you can show that it's a one-to-one mapping rather than the group. So you basically, identify your...
It's like you take the average over G.
Yeah. And in terms of what you just said at the end about the grid, like there is some subtleties that we are assuming that it's on, like there's a classical imaging assumption that we're it's on continuous, so you can apply, without introducing anything extra, like doing rotation. Okay, you probably won't like the next slide then. So so how do we expand that? So rotations. Okay, we're familiar with that in 2D space. Now let's say, we're looking at a optical imaging problem. So this is for example, a picture of a chapel, and then let's say you're standing in this chapel and you turn around in 3D, and then you take an image on the image plane. Then this is what you would call in classical computer vision like a homography or a projective transformation. But what you're doing in 3D is just rotating around. So if you stand in the same place and if you say the center of the eye or the camera is constant, but then your line of sight rotates, then you can say that this group is the 3D rotation group, which then we hypothesize that can we learn more information and get more from this, intuitively speaking. I mean, it doesn't even have to be just standing in the same place. You can imagine now this it's also a subgroup of the whole homography group, so the kind of projective transformations, and then we can do all sorts of projective or affine shears, and we get this kind of nice subgroup structure. And so intuitively saying that we have access to, we can learn more information. So why am I showing a picture of someone standing there when we're talking about satellite imaging? You can also imagine in satellite imaging that what you see on Google Maps is a very post-processed, very clean image of very orthonormal building, so like buildings at right angles, because they correct the images such that you are looking down 90 degrees at the Earth. But actually, real images, especially when satellites have to move around fast, for example, for disaster response, are imaging the Earth at arbitrary angles, so that we can actually leverage this perspective variability in images, for example, satellite images, and also show that by moving from one place, like a satellite that's moving, assuming that it's far away enough from the Earth such that you're not getting anything from the occlusions, then this can also be rated by the same group. So here we're just working on the satellite imaging problem that I showed in the third slide. So we're doing 16 times undersampling of the measurement, so a very challenging problem. And And yeah, so kind of adding these larger groups, so not SO2 anymore, because it's 3D rotations, we're improving the performance when we're doing the learning. It's interesting in this particular literature, in pan-sharpening literature, there's been some deep learning research in it, but if you read the deep learning papers in this particular satellite imaging literature, you can boil down all their loss functions to do this measurement consistency. So they have to do some kind of tricks and hacks to try and learn something, but really they should be thinking the fact that there is a null space operator. But yeah, here obviously we're to do that transformation ourselves when we apply it, then we have to we have to discretize and interpolate, and it is imperfect. So going back to dynamic MRI example, which I used to motivate the talk as well, now we can use some other kind of beliefs that we have. So before, this was kind of beliefs that we have of the imaging system, so the way the satellite interacts with the Earth. Here we want to use some beliefs that we have, for example, that I said with the knee before. So in image registration, in the medical imaging literature, people use smooth or some kind of warping to perform image registration. So, for example, when you want to do brain analysis, you have to morph the brain into a standard atlas so that you can do the analysis very easily. But because of that, we can use that as an assumption. We can say that because we have soft tissue, we can assume biologically that the set of all of the images, or all of the hearts, for example, is invariant to this group of diffeomorphisms. And also in the dynamic context, we have a time sequence of a heart, and then let's say we step that forward by one time step. That is also plausibly a video of a heart. So here we're kind of like building a zoo of different kind of transformations to use. And then for kind of applications of the future, then you pick what you believe. So this becomes akin to kind of the data augmentation zoo that you use. So we're doing this now on real data and cardiac data from a challenge from 2 years ago. But then this challenge was all supervised models. So this is where we're getting the ground truth from. But here now we're training without ground truth. And then we're not far off the supervised learning performance. And we are really recovering high quality videos. Okay. So I might speed up a bit for the last few slides. So we're changing topics a bit. I want to talk a bit about our open source software. So,
wait, before you go on, so
yeah.
how do your techniques compare with like ambient diffusion on things like self-A?
Yeah.
Also equivariant?
I've not done a comparison to ambient diffusion. No one has yet. I mean, I think you compare to SSDU, but that's definitely future work. This is what we envisage. It'd be really cool to compare the trade-off between perceptual quality, like distortion, and inference time. So they have real things.
Just to be clear, though, right, in ambient diffusion, you're doing some corruption operator to the A operator, but you could also train with equivariance to sort of do that. Like, these are orthogonal ideas.
Yeah, yeah.
Right? Like, you're just saying, I can increase the space of my training set by considering equivariance in my data, which depends on the A operator.
Yeah,
like,
yeah.
If you don't want them to commute.
Yeah.
And now that's like you have a bigger training set of unsupervised samples. They're independent ideas.
Yeah, but I'm saying, like, I would be surprised if you took, like, the ambient training set and just, like, are you saying just rotate all the images a bunch of times?
But you're not rotating,
No.
You don't have images to rotate. In the loss function, you add another loss term
that enforces this equivariance.
Yeah.
Yeah, okay, but
That's
it's
what
not a data augmentation.
It's not a data.
That's a regularization. Yeah,
Right.
I understand.
Yeah.
Cool. Okay. Last 5 minutes. So talking about software. So there's a lot of cool research in inverse problems just at ISP, and lots of cool stuff going on. And pretty much everyone's using deep learning. Pretty much everyone's using deep learning. So we provide a library which we like to think is a general framework to include all frameworks right now for including deep learning and image reconstruction. So now that you're familiar with inverse problems, you can see how this fits into the framework. So you have your data sets of X, for example, and then provide simulation operators, so which we call physics. So, for example, MRI, satellites, microscopes, for which we get the measurements. So the top one is a brain, the second one is a satellite image, and the third one is a cryo-electron microscopy example. And then our measurements here are, for example, very noisy or artifact contaminated. And then we abstract all deep learning solvers into this reconstructor, which is kind of your model. And then we have the key parts of experimental pipelines for research in this field. So loss functions, which I've talked about, different kinds of frameworks for models, and the neural networks themselves, and then, if needed, sampling or optimizing, sampling from or optimizing these models. So it's a 2-year-old library now, kind of being developed in parallel with research. Because it's an open source project, it's not like confined to a lab or something. We have a global community with, so at the start it was Europe focused, but now we have users and contributors across like China and the US now, and always trying to reach out to more users and contributors. So the idea isn't that it's like you just give or you just take, the users take and the contributors give. With the community, the idea, the kind of philosophy is that by using it, you're benefiting from it. By submitting your own code to the library, you're benefiting the community. But why do you want to do that? Because it's another way also for you to disseminate your research. So we're trying to stay on top of the state of the art. If we have research contributing their state of the art, then we can, we have this collection of what is the state of deep learning and image reconstruction literature. We have very nice documentation. We place a lot of importance on the documentation because we think that's kind of the real barrier to getting started with these kind of things. You can install it very easily. We subscribe to Modern Python, and we have a Discord channel as well. So just to summarize the motivations of why we want to do this. So the first is probably most relevant to us in this room is, as machine learning researchers, if the state of the art is very easily accessible and trustworthily implemented, this will accelerate your research in that you propose a method. Let's say you propose a loss function or one small part of a diffusion model. You have this framework where you can easily modify one small part and compare to everything else that's been proposed. So secondly, when I say pretty much, so kind of people making imaging devices now or of the future, let's say tomorrow they invent a very fancy new imaging device, they might not necessarily have the resources or know how to start using deep learning or have the tools to start using it. So we also want to benefit these people. So in a way that, let's say you come with a new physics operator, a new machine, you can just replace that and then still benefit from all of the state-of-the-art parts of the framework. And then finally, we're encouraging reproducibility. You can have a browse. We have user guide and lots of examples. Okay, 2 quick examples maybe now. So what do we want to do now? So there's lots of stuff that I've missed out whilst doing this presentation. There's lots of research, and just for my own personal research, I'm interested in loss function. So if we keep everything else the same, and then just vary the loss function, can we use the loss function to solve these problems? So equivalent imaging was one example, but there's lots been proposed in the past few years, and I want to benchmark these, and I think that'd be useful. So that's kind of some ongoing research. Another ongoing research idea is kind of parallel to the diffusion model research. Can we train a feed-forward network very well across different modalities such that it has generalization performance outside these modalities? And the kind of hypothesis here is that if you train enough on different problems, so for example, train on motion blur problems, Gaussian noise CT problems, and single core MRI problems, can we have generalization outside this performance? And I think that's a very promising direction. So in conclusion, I presented to you what an imaging inverse problem is and why we need unsupervised learning, so learning without ground truth. Why this particular set of loss functions called equivariant imaging performs well in certain scenarios, which are real-world scenarios with real data, which we've tested on 2 examples, including using real data. The food for thought here is like, what are the scenarios and what are the, so like an engineering perspective, what are the scenarios, but mathematically, what are the groups that can we think about? So for example, permutation groups, can we not do imaging anymore, do graph-to-graph problems and use a permutation group? That could be cool. I've talked about open source software for doing this, and a couple of directions. Cool. Thank you.
Any other questions?
So, I was a little confused. So, any diffusion model include the yes or no?
In the library?
Yes.
Yes. Yeah, I didn't go too much into depth in this presentation, but yes, so there's kind of 3, well, it's the same framework as what I said earlier. So we have starting from the iterative methods, so we have kind of classical iterative optimization, and then like plug and play, for example, replacing parts of that with a neural network. And then we have sampling from a diffusion, so with a diffusion model, and then have a data fidelity, you specify the data fidelity, for example, DPS, and sample from that. We do have that. And then we've got feed-forward networks.
And how do they perform in your table?
In terms of research, I've not compared to it yet. I think that's a very important direction, very near future work. But then it's also a question of how do you fairly compare like generative or iterative methods to feed-forward methods. Because you have to match you have to match the number of parameters of the neural network itself. But then also with feed-forward methods, like an unrolled network, you can still increase the number of iterations. And obviously a diffusion model, you have to do, for example, hundreds or thousands of iterations. So I don't know what the best way to go.
Acceleration, that's not true. You have lots of distillation methods.
Yeah.
Make it to be a single step, few step generation.
Yeah. There's a lot of research, yeah.
So I don't know much or anything about.
You seem to know a lot.
But so to which extent is your method dependent on the fact that the map from the data to the image is linear? You named Fourier transform as an example, and I guess that the linearity comes just from the physical setup of the machine. But
yeah, all the theory is for linear operators so far. I think there is some work in not our group, but to generalize this in nonlinear problems. For example, like a phase retrieval problem where your forward problem is you take the complex magnitude, but I'm not too sure on the actual results. But yeah, I mean that goes beyond me. How would you show that? But I encourage you to read I've not put them in the presentation, but there are a few follow-up works with some more theories in.
Any other questions? All right, thanks again.
Thank you.